How we doing?
Good.
We're doing.
We're doing?
Yeah. We're doing.
That's good news.
Can't wait for break.
I know. Next week. It's exciting. Wait, including today, we just have 6 class periods
That's crazy.
left. So I do want to mention my plan for the final. So I think your final will be in 2 parts. One part will be the comprehensive part. I'm going to have you come in and do an oral exam. So your oral will be the comprehensive part. So basically, not anything long proofs. What I'm looking for would be understanding what a definition is, being able to provide an example of something, maybe a short proof, but nothing long proof.
So is that like on paper too then?
Nope. You come in and actually say things that,
Okay.
and if you need to, write on the board kind of thing.
Okay.
So I'm thinking like 20 to 30 minutes, something like that. So, and then the other part will be like self-scheduled, like we have been doing, for the, and that'll just be over the group stuff that we've started. Okay, so you haven't been tested over that yet. So the test that you'll actually do a test on will be that. The other part will be come in and have a conversation with me.
And then, wait, so there's no like specific like final time?
No, well, no. I was just have you schedule both of those with just come with me. I just asked you to schedule it by the Wednesday of finals week. Okay. I think technically ours is scheduled on Tuesday, but you can just schedule it whenever. Because you'll actually schedule 2 different times with me then.
Both during finals week, though.
If you wanted to do it the week before, you can.
Okay.
I'm going to put together topics for you to go look at. Look at like what definitions do I expect you to be able to do, what kind of examples do I expect you to be able to give me, that kind of thing. I'll get that written up probably by the end of the week, and then you'll have it. So if you wanted to do that part at the last week of classes and then the other part during finals week, that's fine.
Thank you.
Mm-hmm. Yeah. So that is the plan. So don't forget you had an assignment that I gave you. Not last week, the week before, since we didn't meet last week. So it was those few problems over group theory that I'd given you over on page 201, I think it was. So you can give those to me on Thursday. I was just reminding, since you may have forgotten that we actually had that, since it's been a while since we chatted. All right. So are there any questions at all for anything? I posted an answer key too for the exam if you want to go back and look at that. It's under, apparently I hadn't made up a section for it on Moodle, so it's just posted at the bottom of exam reviews. So if you go on Moodle, it's at the bottom of that. Probably the very, very last thing that's on the page. So, but I'm happy to go over anything. I think if you go through the key, you'll see basically a lot of it was definition type of things. For example, on the problem with the homomorphism, that went from polynomials with real coefficients to the real numbers. The first question was showing that was a surjective homomorphism. The second part was asking how you know the kernel is maximal. Well, remember, first isomorphism theorem says that if you do ring mod out by the kernel, it's isomorphic to its image. So since you'll have R of X mod out by the kernel will be isomorphic to R, then since it was surjective, R is a field, so the kernel has to be maximal. Basically remembering those concepts. And by the way, that's the kind of thing that I'm talking about when you come in and have a conversation with me, remembering those kind of things. What does the first isomorphism theorem say? How do you know that a ring is an ideal? How can you show using quotient rings that a ideal is maximal? That kind of thing. That's what I'm saying about just kind of testing concepts or remembering concepts, understanding definitions, understanding what a theorem says, that kind of thing. Okay. Anyway, let's continue on then with our group discussion. So last time we did lots of different definitions. One of the ones that we did was order. So let's remind ourselves order. Remember, there's order of a group and order of an element. There's a difference. They use the same word. We use the same notation. But what does each one mean? Order of a group just means what? Yep, good. So that's just number of elements in the group. It's just cardinality of a set. So you've done cardinality of a set in discrete before. At least I assume you've talked about it in discrete at this point. Cardinality of the set is just how many things are in the set. It's just a different word. When we talk about group, we talk about its order rather than its cardinality. Versus order of an element. What is order of an element in a group?
The smallest positive integer, such that the element raised to that integer is the identity.
Okay. I'll say smallest positive integer n, such as a to the n is e. If no such n exists, then A has infinite order. It's how many times do you have to operate an element with itself to get back to the identity. So let's do a couple of examples of finding orders. Pardon me. Remember, we've got some different notations for things. You have U sub 8. Remember, this is the group of units in Z8. So it's the elements that have multiplicative inverse. Multiplicative inverse says. So the operation here is multiplication, not addition. You're welcome. So this particular problem, and this is, by the way, this is number 7 in your book on page 201. It asks for the order of the element 5 in this group. So again, to calculate the order, basically, a lot of times we will have a couple of theorems that'll tell us about things here later. But typically we brute force it. Okay? So, well, certainly 5 is not 1. Right? So the order is not 1. So do 5 squared. What do you get when you get 5 squared? You get 1, right? Because you're going to square 5, you get 25, mod 8 is 1, right? 1 is the multiplicative identity. So what's the order of 5 in this case? 2. Yeah, good. Okay. So again, when we use this notation, we're looking, remember the units in Z mod n are the things that are relatively prime to n. When we're talking about the unit group, we're talking about under multiplication. Okay. When we do the operation in Zn and talking about it as a group, we're always going to be talking about addition. Okay? So make sure you keep those things straight. If you're just talking about groups, one operation. If it says Zn, we're going to assume that the operation is addition then. Okay? But if we talk about Un, that's the multiplicative group of units. So the operation there will be multiplication, not addition. In particular, we don't want to use addition for units because it may not be closed. If you add 2 units together, you may not get a unit. Okay. For example, if I add 1 and 5 together in Z mod 6, I get 0, which is certainly not a unit. But 1 and 5 both have multiplicative inverses mod 6. Okay. So I just want to make sure we're keeping track of the operation. Remember, for groups, we only have one operation. Okay. Typically, it'll be addition if it's Z mod n. It'll be multiplication if it's a unit group. If it's a matrix group, it may be addition or multiplication. You have to read it carefully. Okay. And if it's our permutation groups like Sn, It'll be function composition. Okay. So along those lines, it asks us to find the order of the permutation that looks like this. In S7. Now we're going to study Sn a little bit more in depth in a couple of sections down the road. However, one thing we talked about before we had our hiatus was how to change this over to cycle notation. Right? This is our permutation notation where we're just talking about each input gets mapped to what output, right? So 1 gets mapped to 2, 2 gets mapped to 3, and so on down the line. But remember, we talked about how we can convert that over to cycle notation. So remember, we start with 1. 1 gets mapped to where? 2. So we write that next, and then we figure out where 2 gets mapped to. 3. Figure out where 3 gets mapped to. 7. And then when 7 gets mapped to 6. 6 gets mapped to 4. 4 gets mapped to 5. 5 gets mapped back to 1. And we close off the cycle. And we're doing that. Okay. One of the reasons we like cycle notation, we can easily read the order of a cycle by simply looking at the length of the cycle. What's the length of that cycle? 7. So what's the order of that element? 7. Good. Exactly. So the order of this would be 7. And it's not too hard to see why. Remember that we have to figure out how many times we would need to compose this function with itself to get back to the identity. Well, the first time, if I do the function twice, you would get, this just says 1 goes to 2, so that's why the first power doesn't work. If I do it twice, I would get 1 goes to 3, 3 times I go to 7, 4 times I go to 6, 5 times I go to 4, 6 times I go to 5, 7 times I finally get back to the identity, right? So that would be, this was what the function does. If I do this and then do it again, I end up here. If I do it again, I end up here, and so on down the line, right? It takes me 7 times. I have to do, I think what is f is my function. I do f of 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 x, right? To get back to the identity. I have to compose it with itself 7 times. Okay. And that's true for any cycle. Another reason why we like cycles, and we're going to prove this later when we get to the section, but we can go ahead and do it now. If we have disjoint cycles, if I have disjoint cycles, then the order is going to be the least common multiple of the orders of each cycle. Like I said, we'll prove this later, but this is another reason why we like cycle notation. I can get the orders quickly. The order of 1, 2, 4, 6 would be 4. The order of 3, 5, 7 would be 3, and the least common multiple is 12. Yeah. Does that make sense? I mean, like I said, we'll prove that later, but it makes sense. Well, the reason why it works is because disjoint cycles commute with each other. So if I raise this to the 12th power, I'd be raising each of the, to the 12th power, composing it with itself 12 times. I would do this with itself 12 times, this with itself 12 times. But every time I do this with itself 4 times, I end up back to the identity. Whenever I do this one with 3 times with itself, I end up back to the identity. So 12 works for both of them, and nothing smaller will work. So that's why we get least common multiple for those. It also allows us to figure out what your possible orders of elements are in S7. So if I can always write my cycles in disjoint cycle notation. So what are the possible types of elements we could get? Well, we could get a 2 cycle all by itself. You could do 2 cycles that are disjoint, or you can do 3 2 cycles that are disjoint, right? That's the only ways you could do 2 cycles and keep them disjoint, right? Because I only have 7 symbols to play with in this case, right? If I want to make sure they are disjoint, I could put a single 2 cycle or 2 2 cycles or 3 2 cycles that are disjoint, but I can't add a 4th 2 cycle if I only have 7 symbols. Because I wouldn't be disjoint anymore. But if I do 1 or 2 or 3, a 2 cycle has order 2. If I do 1 or 2 or 3 and they're all 2 cycles, what's the order going to be? 2, because the least common multiple of 2 and 2 and 2 is 2, right? I could do a 3 cycle. I could do another 3 cycle with it that's disjoint, but that's the biggest I could get for 3 cycles. But each 3 cycle only has order 3. So again, if I did disjoint 3 cycles, I would also get order 3. If I have a 4 cycle, I can't put another 4 cycle with it, but what else could I put with it and keep it disjoint? Worry about the disjoint part. If I had a 4 cycle, what else could you put with a 4 cycle? A 2, a 4 and a 2. If I put a 4 with a 2, what would the order be? 4. If I put a 4 with a 3, I get 12, like this one is, right? If I do a 5 cycle, that has order 5. What else could I put with a 5 cycle and keep it disjoint? A 2, a 5 and a 2 together will make 10, right? So I get order 10 for that. If I do a 6 cycle, I can't put anything with it because a 1 cycle is just the identity, right? I can't put anything with a 6 cycle, so I'd order 6, or a 7 cycle would have order 7. So this 12 turns out to be the largest order element that I can have in the group. The biggest possible order we can get. Now, the order of S7 is huge. What is the order of S7? What's the order of any Sn? Call it a permutation group for a reason. It's n factorial, right? So it'll be 7 factorial, which is 5,040. So even though there's 5,040 distinct elements in S7, the largest order you could ever come up with is 12 of any particular element. We're going to talk more about that later, but I'm just going to try to preview that stuff when we do a little bit more analysis of these particular permutation groups. Is that okay? But again, this is why we like the cycle notation, where we can read off things a little bit more easily in this case. Let's do another one. Again, this is, like I said, this is number 7 on page 201 if you want to look in the book. They write their matrices with parentheses rather than brackets. I don't really care which way you write it. The matrix 0, -1, 1, 1 in GL2R. Remember what that means again? It's the general linear group of 2 by 2 matrices with real entries. That's what GL2R means. General linear group means the determinant is not 0. The reason why we want to make sure our determinant is not 0 is because we want to make sure the matrices are invertible. So this is going to be a group under multiplication. Okay. So again, I would just start by brute forcing. Multiply the matrix by itself. We get what? -1 here. 0 up here. 1 here, and it's interesting. It's not 0 up there. That's the problem. It's -1 here. 0 here. Sorry about that. Not back to where I started, certainly. But notice that it doesn't necessarily look like it's going to get bigger indefinitely. if I would have gotten, say, a 2 when I multiply these things together somewhere, the entries look like they might be getting bigger. And if I do it again, I might get a 3. If I do it again, I might get a 4. And I'm probably never going to get back to the identity. But at least this one, I kept 1s and -1s. So I still got a little bit of a shot of getting back to where I started, or getting to the identity, I guess I should say. So now if we do this thing cubed, bless you. We get what? -1, 0, 0, -1, it looks like. And now you might be able to guess what we need to raise the matrix to get back to the identity. Because what is that particular answer we just got? Is that the identity? No, but it's the not quite the inverse, but it's the additive inverse, right? It's the negative of it. Okay. So if I cubed my original matrix and I got to that matrix, the opposite of the identity, what power do you think I need to raise the original one to get back to the actual identity? 6, right? I need to square it, basically, right? So we should get this thing to the 6th is equal to the identity. And you can check that 4 and 5 don't work. Because again, remember, it has to be the smallest positive integer. Well, we know that, but we did prove last time, we did prove last time that if you raise at something to a power and you get the identity, then the order of the element divides the power that you used. So what I mean by that is, if you had a to the 12th as the identity, for example, that does not guarantee that the order is 12. All that guarantees is that it's at most 12 and that it divides 12. So all this tells me is that the order of A is 1, 2, 3, 4, 6, or 12. Okay. I don't know right away that saying that it is the 12th power gives me the identity. It means the order is 12. It just means it divides 12. Okay. Now, if this were a prime power, and the element's not the identity, then you would get the order. Because two things that divide a prime are 1 and the prime. And the only element that has order 1 is the identity. Okay. But all we know about from this statement is that it divides, okay? So again, from this statement, I would know that the order divides 6, but we already showed that 2 and 3 didn't work. So it had to be 6. It's not 1, it's not 2, and it's not 3. So it had to be 6. We eliminated the other cases. So you don't actually have to check 4 and 5. Because 4 and 5 don't divide 6. All right. Now notice that we get a group, we get an element of finite order in this particular group, but you can find elements of infinite order in here pretty quickly. If I do this to the nth power, it's not too hard to see that you end up with that. It's not too hard to see that you'll end up with that. You can do it by induction if you really, really want to. But notice if you just square it, you'll get a 1 in the upper left-hand corner. You'll get a 2 in the upper right corner. You'll get a 0 and a 1 in the second row. Do it again, you'll get a 3. Do it again, you'll get a 4. You'll end up with an n. So am I ever going to get back to the identity if when I raised it to higher and higher powers, that entry is always going to get higher and higher? No. Okay. So this will have infinite order in that case. So we get a group here. The general linear group has elements of infinite order and has elements of finite order. That was kind of the whole point of me talking about that. Any questions on that at all? All right. I don't think I want to do that one. And I already did that one. Just trying to see what kind of problems I'll do. I want to do a couple of other proofs, though, real quick before we go on to subgroups. This is number 19 on page 202. This one says that if A and B are in a group G, then the order of B, A, B inverse is the same thing as the order of A. Now, what's going to be really, really helpful in order to be able to prove this is the following. Can't remember if we've talked about this before in here, but this is certainly a property that's not too hard to see. How does that simplify? Where does that N end up going? To the A, right? Because if you think about how this gets written out, you'd have BA B inverse times BA B inverse, BA B inverse times, right? BA B inverse. And what's going to happen here in the middle every single time? What are those going to end up multiplying together to give you? The identity, right? We would use associativity to regroup and put the B and the B inverse together, get the identity, and then it just all smashes together, right? So you can see that all the B inverses in the middle all collapse to the identity, and you end up with B A to the N, B inverse. Does that make sense? Okay. So if we know that A to the N is the identity, then BA B inverse to the N would also be the identity. Okay. So if I know that when I raise A to the nth power, I get the identity, I get the identity when I raise BA B inverse to the nth power, right? Because I just move the n to the inside and then replace it with the identity, and I'm done. Okay. Now, what does this say about the order of these two elements? And I'll give you a hint. It does not say they're equal yet. Okay. If I start with A to the n as the identity, and I show that this raised to the nth power is the identity, it does not tell me that they're equal, right? Because remember, again, the order is the smallest positive integer that works, right? I just know that this one works, correct? So the order of this, if n is my order here, then all I can say that was my order is at most this, the same as that one, okay? So if, to write that down, if the order of A is n, then what we just showed is that the order of B inverse is less than or equal to n. It's not necessarily n. All I know is that n's the biggest possibility. Remember again, the order isn't just a number that works, it's the smallest one that works. Does that make sense? Okay. So I need to go the other way. Oops. So start with the order of BA B inverse being some other number. I'll call it M. That tells me that when I do BA B inverse to the nth power, I get the identity. What can you do with the M now? So I get B A to the M B inverse equals E. Now, can we get a to the m all by itself on the left-hand side? Or more specifically, what do you need to do to get a to the m all by itself on the left-hand side?
You can multiply the left by b inverse or on the right by b inverse.
Yeah, okay, exactly right. So you're exactly right. I need to multiply on the left by b inverse and on the right by b. If I want to get a to the m by itself, I need to get rid of the b and the b inverse, but I got to make sure I do it on the correct side. I don't know that we have commutativity, right? I don't know that the group is abelian to start with. I'll be precise to start with. Since we're multiplying by b inverse on the left, you get a b inverse on the left of the identity on the right-hand side. Since we're multiplying by b on the right, I'd have a b on the right of the identity on the right-hand side. However, the right-hand side, it doesn't really matter, because what's that going to simplify to on the right? E. And the left-hand side simplifies to a to the m. So now I get, notice in the first case, we got the order of BA, B inverse was less than the order of A. We've now reversed it, didn't we? This now says that we have the order of A is less than or equal to the order of BA, B inverse. Oops. Above, we had order of A was greater than or equal to BA, B, order of BA, B inverse. So what has to be true? It has to be equal, right? Is that okay? When you do this kind of thing to an element or this kind of thing to a group, if you multiply on one side by an element and then multiply on another side by the inverse of the element, you refer to that as conjugation. So we're doing a conjugate of A. Conjugation has some important applications that we are not going to talk about because it's higher up than what we'll do in this class. But we call it conjugate. We did this in linear as well towards the end of the semester when we talked about diagonalizing matrices and using eigenvalues and eigenvectors to diagonalize a matrix. We called it similar in linear algebra. It's the same kind of idea. Okay. All right. Let's do at least one more here with orders. This is number 30. Says that if A and B are elements of G, then the order of AB must be the same thing as the order of BA. I mean, this is hopefully very obvious if A and B commute, since AB and BA would be the same element. However, it's interesting that the order part works even if it's not commutative. It's kind of nice that it works this way. So again, we're going to use the same kind of premise that we did basically right here just a second ago. If you have AB to the nth power equals the identity. Let me ask you the first question. Can I distribute the n over the product? Can I write that as, is this the same thing as this? No, not generally, right? This implies that A and B commute. Or at least there might be some powers of it that commute, right? I can't do this generally speaking because that implies commutativity, right? Right. However, I can write this as AB, 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 dot, 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 AB equals the identity. And I would have n factors of AB in that. Can you, and I said we're going to do something similar to what we did up here, right? Can you figure out what to multiply on both sides by so that I see n powers of BA rather than n powers of AB?
Multiply by A inverse on the left.
Okay. And then the A inverse on the left. I want to see BA though all the way across. What do I want to multiply on the right? A, right. Good. And notice basically what have we done? We canceled the A on the left and added one on the right. And what happens on the right-hand side? It just says its identity. Good. So this becomes BA, BA, dot, 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 BA. Or BA to the nth power is E. Okay. So notice that if AB to the nth power is E, then BA to the nth power is E, and these steps would be reversible, wouldn't they? I can work backward and get the other way around as well. So basically, this is the proof to show that the orders are the same. I can work backward up the chain and get back to the same place where I was. Well, I mean, it's a little bit different, right? At this step, I would multiply by B inverse and B, but it's the same idea. Okay. So we really do get that the orders are the same. Okay? Right. Pardon me. All right. So let's go on and talk about subgroups a little bit. So this is section 7.3. So we've talked about subrings and we talked about ideals back in rings. So this is the same kind of concept. When we talk about something being a subgroup, it's going to be a subset that's also a group under the same operation. Okay? So as a definition, we're going to let H be a subset of G. Then H is a subgroup of G if H itself is a group under the same operation as G. Remember, groups only have one operation, so we're just talking about the same operation. So we're not going to have that whole ideal notion where we had to absorb multiplication and be closed under subtraction. Okay, we only have one idea here. All right, how about some examples? So let's say we do the operation as addition. We look at the integers and we look at the rationals. Under the exact same operation, do we add integers and we add rationals the same way? Sure do, right? Under the same operation, Z is a subgroup of Q. I don't remember if this book uses the notation or not, but this is pretty common notation for subgroup. We will use a less than or equal to sign for subgroup. This is pretty common notation for subgroup.
That won't get confusing.
I don't like that.
You don't like that, I'm sorry.
Disapprove. Try again.
Another example. Remember our dihedral group, D4? Remember D4 had 4 rotations and 4 reflections. If I put all the rotations together, I get a subgroup. I also get, if I take any reflection and add the identity in there, and just use those 2 elements, I will always get a subgroup as well. Because what happens when you do any reflection and operate it with itself? What do you get? In D4, if I take a reflection and do the exact same reflection again, where do you end up back to? The identity, right? So if I use any rotation, not any rotation, if I take any reflection along with the identity, then I get a subgroup as well. Okay. If I take the identity and R180, I get a subgroup. Because what happens when you do a 180 degree rotation and do another 180 degree rotation following it? Get it back to the start, right? Okay. What's interesting is there are some other 4 element ones that are a little bit different. You should check if you do R0, R180, a horizontal reflection and a vertical reflection, you also get a subgroup. And if you change out the horizontal and vertical and just put in the 2 diagonal rotations, you'll also get a subgroup. You should check to make sure that works. Probably the best way to make sure that works is just create a table for it. Just create the 4 element table, like we call it a Cayley table. Another one. Oops. Remember our special linear group are the matrices, the n by n matrices with determinant equal to 1. General linear group is just determinant is not equal to 0. The n again tells you the size of your matrix. The f is just standing for any field. The reason why we need fields is because we need to make sure we can do multiplicative inverses. So we'll make sure that we have elements coming from a field for our entries. Then we get that subgroup notation, subgroup relationship as well. Okay. So, got some examples. There's lots of different examples of those things. A lot of times we'll be interested in being able to prove something is a subgroup. So we have a few, what we refer to as subgroup tests for those. We have a 2-step subgroup test. We'll also have a 1-step subgroup test. And we'll also have a finite subgroup test. So let's just go through those real quick. It's 2-step. So remember when we first did subrings, we said that it needed to be closed under addition and closed under additive inverses and then multiplication as well, right? But we had to do addition and then inverses, additive inverse, make sure they had both of those in there. And then we said, well, really, instead of just doing addition and inverses, we could just do a closed under subtraction. That's the difference between the two-step subgroup test and the one-step subgroup test. Okay, so the two-step subgroup test says, let's let H be a subset of G with H not equal to the empty set. Then H is a subgroup of G if and only if 1 AB is back at H whenever A and B are in H, and 2 A inverse is in H whenever A is in H. It's closed under the operation and it's closed under inverses. That's the two-step subgroup test. Certainly, we have an if and only if, but certainly the forward direction makes sense, right? If it's a subgroup, then it has to be a group, which means it has to be closed under the operation and have inverses, right? Right, we need closure and have inverses. The other way is the important way. Okay. The other way is if we have these two properties, then we know it satisfies all the group axioms. Remember, your group axioms say that you have to have associativity. You have to have a two-sided identity with respect to the operation. And you have to have a two-sided inverse for every element, right? Every element has to have an inverse. Okay. All right. So the forward direction is just because we assume it's a group, and then we're just saying, hey, it has group properties. Okay. So really, we want to go the other way. So, pardon me. So let's go the backward direction. That's the important direction. Now remember, we're saying that something is not empty. Okay? So right away, we know something exists in H. Okay? Right? Okay. We need to show that it satisfies all of the group axioms. Okay? Well, remember again, group axioms are operations associative, have to have an identity, have to have inverses. Well, we're using the group operation, right? If it's a subgroup, it has to be the exact same operation. So is there anything to prove for associativity? No, because we already have an associative operation. The group operation is associative, right? We also have to have inverses all the time. Well, if we're assuming the other two conditions are true, do we always get to the inverse of every element? Look at the second condition. This is if A is in H, then A inverse is also back in H again, right? So do we have inverses? Yeah. So the only thing we really need to make sure we have is that we have an identity, right? What's the most likely candidate for the identity of H? What do you know already has an identity? G already has an identity, right? Because it's a group, right? So the most likely candidate for the identity of H is the identity of G. It better be in there. Okay. So let's write all of this down. Since the operation on H is the same as the operation on G, the operation is certainly associative. Also, by property 2, every element in H has an inverse that's also in H. So we just need to show that the identity of the group is in H. That's really all we need to do. Okay. All right, so property 2 says that if we start with something in H, and this is why we need a non-empty thing, property 2 says that A inverse is in H. What can I do, and what property am I going to use to show that the identity of G has to be in H? What should I do with A and A inverse to get the identity? Yeah, just multiply them together, right? And property 1 says that that means it's back in H, doesn't it? The product is back in H. When I multiply them together, I get the identity. When anytime we multiply two elements of H together, I'm land back in H by that property 1. So the identity is in H. Hence, H is a subgroup of G. So let's see if we can put this together to show that something is a subgroup. Let's look at, this is number 15A. On page 211. Number 50, it says that if we have two subgroups of a group, their intersection is also a subgroup. Okay, so let's see how this two-step subgroup test works. Okay. Oh, okay. The first thing we need to make sure is that we have something that is not empty, right? We need to make sure something is in there, correct? So what do we know for a fact is going to be in H and in K? What will they absolutely have in common? What specific one? The identity has to be in both, right? So since E is in H and E is in K, we have that E is in the intersection, and the intersection is not empty. Okay. That's usually the thing you're going to show is in the subgroup, by the way, is the identity had to be in there so that you get it's not empty, and then show that it really is a subgroup. So with the two-step subgroup test, we'll start with two elements in the thing that you're purporting to be a subgroup. Okay, so we'll start with A and B being in our intersection. So let's just go through it. I want to show that A times B, or A operated with B, is back in the intersection. And I want to show that A inverse is back in the intersection. I want to show that it's closed under products and closed under inverses. So let's just go through and see what happens. If we're assuming that they're in the intersection, then where does each one have to live? In both. Good. So A and B are both in H, and A and B are both in K. But what are we assuming that is true about H and K?
In G.
and specifically what type of things in G? Subgroups, right? There's subgroups of G. If it's a subgroup, the important part of that is that it's a group, right? Okay, so since it's a group, what can we say about A operated with B? Where does it have to live? Well, that's where we're trying to end up at. True. Was even better than G. Is it H, right? And it's in K, correct? Because they're both subgroups. So since H and K are subgroups of G, we have AB is in H and AB is in K. Well, if AB is in H and AB is in K, it lives where? In the intersection, which is where we wanted it to live, right? Remember, we're trying to use that two-step subgroup test, starting with two elements in the intersection to show that their product is in the intersection. Also, since H and K are subgroups, where does A inverse live? If A is in H, where does A inverse live? In H. And where else does A inverse live? In K. Good. So that means it's in the intersection. So since the intersection is closed under products and closed under inverses, it's a subgroup by the two-step subgroup test. We'll do another one of those here in a minute. But let's write down what the one-step subgroup test is. And then do a proof with that. Same setup. We're going to let H be a subgroup of G with H not equal to the empty set. Then H is a subgroup of G. Good grief, I can't write today. If and only if AB inverse is back in H whenever A and B are in H. Remember again, this was kind of our one-step test to show that something was a subring, right? Because rings, remember the group operation part is addition. So doing the inverse of an element really means you're doing the opposite of the element. So for subrings, this is the same thing as A minus B. It's just written additively versus multiplicatively. Okay. So again, if we can do this all in one step, then we're done. Okay. Basically, you use the two-step subgroup test to show the one-step subgroup test. Notice that we already agreed that the identity is always in every subgroup you're going to do. So if the identity is in there and B is in there, if we have this property, then B inverse is in there. And then the original, so then you just go through the whole spiel of the two-step. I'm not going to go through the proof because it's literally just write out the steps of the two-step subgroup test to apply to this situation. Okay. But again, the identity is in H, B is in H, then you would get B inverse is in H. So it's closed under inverses right away. Right? And so then to get that it's closed for the product of anything, well, if it's closed under the inverses, then I would do A. If A and B are in H, then B inverse is in H. So then A, B inverse would be in H, or A, B would be in H. And so we close under products. So it really is just the proof of the, or just use the two-step subgroup test to prove the one-step subgroup test. So let's use the one-step subgroup test for a particular problem here. Oh, let's look at, this is actually in the book, theorem something or another. 7.15. Nope, not 7.15. 7.13. Sorry. I'll need to write down a definition here in a second. But theorem 1.5 or 7.13 says that the center of a group is a subgroup. So what do we mean by the center? The center is the set of things that commute with everything else. So to give a quick example, the identity will always be in the center, obviously, because our identities have to be two-sided identities. But remember when we did our operation table for D4, the 180-degree rotation commuted with everything. So as an example, the center of D4 is R0 and R180. Okay. Again, it's the set of things in the group that commute with absolutely everything else in the group. Not just a few things, but absolutely everything in the group. Okay. All right. So again, to use any of your subgroup tests, you need to make sure your purported subgroup is not empty. The easiest thing typically to show that is actually in your subgroup is the identity. In this case, the identity clearly commutes with every other element, right? When we have an identity, it has to work on both sides. So the identity has to be in there. This is going to end up more like one-step or two-step subgroup test anyway. Typically, it's usually what happens. The one-step subgroup test is nice if you're able to use it, but usually to be able to use the one-step subgroup test, you're going to end up with showing something as a two-step subgroup test anyway. So let's show what I mean by that. Let's say that A is in the center. I shouldn't have said that way. The way I wrote this, let's say X is in the center. Sorry, let me flip-flop it around. I only wanted to write it for the same way that I used the definition. If X is in the center, then X commutes with everything. What would I need to do with this equation that we have to show that X inverse also commutes with everything?
multiply by x inverse on both sides.
Yeah. Good. Yeah, multiply the x inverse on the left and on the right, right? So multiply on the left and on the right on both sides. How does the left-hand side simplify?
Just x inverse a.
Good. And the right-hand side simplifies as?
X.
Good. And again, this is for all A and G. Thus, x inverse is back in the center. It's messy. So if x is in the center, x inverse is also in the center, is what this says. Okay. So now, finally, to try to use the one-step subgroup test, now let's let x and y be in the center. Then for all A and G, we have I want to show that x, y inverse is back in the center again. That's what the one-step subgroup would say, right? If I start with x comma y. If I start with two elements in my purported subgroup, then the product of x and y inverse has to be back in my subgroup again. Since I want it back in the center again, I need to show that xy inverse commutes with A, given that x and y commute with A. That's what this says, right? So how do I get that this is going to commute with A? What do we need to do?
You would have to equal a times xy inverse.
That's what I want to end up with. Yep, you're exactly right. So how am I going to end up there?
Multiply by a on the left and then a inverse on the right. But I don't know if you could do that.
Yeah, since I don't have an equation to start with, that makes it a little more difficult.
Oh, because we don't.
Yeah, I don't have an equal. I don't have an equal on the other side. That's okay. It's a good thought. That's what we've been doing all day, right? Kind of playing around with both sides. Unfortunately, this one I don't have two sides yet.
Can we say it's equal to y negative 1x a? With that one or not?
I can say that because since x and y commute with everything, they have to commute with each other. I would agree with that. But remember, I want to end up with x, y, or the a on the other side. All right?
Okay.
That's okay. It's what you do. You throw the ideas out and see what happens. Math is messy. What's the first axiom for groups? What does your operation have to satisfy? We have three axioms, right? What's the first one?
Closure.
Well, okay, so again, closure is kind of baked in when you say you have a well-defined operation, but you're right. Okay, so let's talk about the second one. Yeah, it's associativity, right? So how can I rewrite that using associativity?
Just without the brackets.
Yeah, or even better, I can move the brackets, right? All right. We said that if y lives in the center, then y inverse also lives in the center, right? So what can I do inside the parentheses now? Flip it. Good. Now what do you want to do? Reassociate. and then do it again. Yeah, flip the X and the A. And then regroup again. And again, this has to be true for any A. So our XY inverse is in the center. And the center is a subgroup. All right. So the center, again, just remember the center is the set of things that commute with every single other element in the group.
This is maybe like a con. The one-step subgroup test, but it's not one step.
It wasn't really one step, I know. You feel like you're being gaslighted, right? It's just one step.
Find your subgroup in one step.
All right. There's also a concept called the centralizer of an element. And that is, given a specific element, find the things that commute with that element. That's what the centralizer is. Okay. That can be bigger than the center. Just because something is in the centralizer of a specific element doesn't mean that element commutes with absolutely everything else. It just means it commutes with that one specific element. All right. Anyway, any questions on that? I know it was a lot to take in. We'll do more with subgroups next time. We'll probably also get into some stuff with isomorphisms and homomorphisms, which hopefully will go fairly smoothly since we already talked about them with rings. And then we'll also spend some time talking about the SN group a little bit, hopefully. So anyway, we'll see you on Thursday. I won't give you any new problems to work on right now.